After talking about all the ways that you'll lose money in college, we're on alpha, beta, and gamma decays. And now that we're back with Dylan and Connor. Okay, so we're going to talk about alpha, beta, and gamma decays for nuclear reactions. Or for just reactions in general. There's two specific nuclear reactions, fission and fusion. We'll talk about those later. But alpha, beta, and gamma decays do come up a lot. They are important things to understand and recognize and see what's going on with them. So we'll talk about them. The first type of decay that we're going to look at, when we talk about decay, we're really talking about having a massive particle turn into something else. Okay, so we're normally going from massive to smaller things, less massive. And in alpha decay, which we symbolize with the alpha symbol, Decay, learn to spell. In alpha decay is really saying that something is going to decay into an alpha particle and something else. Now, what's an alpha particle? Well, an alpha particle, haha, look at that, an alpha particle, it's just the alpha. It is something with a positive charge. And specifically, an alpha particle is helium. An alpha particle is a helium particle. They are the same thing. So, what we mean by this is that if you're ripping 2 protons off of the nucleus of something, and with it, you bring 2 neutrons as well, or, yeah, bring 2 more neutrons, then what you've done is you've ripped off an alpha particle or a helium. So the way this would look is if we had some element, let's just label it N. It could be any element. That's an element symbol there. We could use an X for that. We could use an N for it. You could actually put an element symbol there, like Fe or Li or H, like whatever. Well, not H in this case. That wouldn't work. How'd you get a helium off of a hydrogen? Anyways, if you have an element symbol there, and recall, an element symbol has a atomic number and an atomic mass number. This element will decay, and this pains me to write this as a physicist, but decay, it yields. It's that chemistry arrow coming back to haunt us. It's going to give us some N prime, not a derivative. How do you take a derivative of something like magnesium? This doesn't make any sense. But what you have here is you have the atomic number minus 2, because you're losing 2 protons, and the atomic mass number minus 4. To this, we're going to add helium, 2, 4. If you wanted, you could have just written this as an alpha, but I like to write it initially as this helium 2, 4, so that you can see the following. What we're doing here is we are going to conserve charge and atomic number and atomic mass number. Note, A minus 4 plus 4 is equal to A. Z minus 2 plus 2 is equal to Z. Notice how we haven't lost anything here. Okay? We have conserved quantities. This is a very important thing for all of our decays. Our basic rules are, technically, we must conserve charge, and we must conserve the atomic mass number and the atomic number as well. So generally speaking, if you have some sort of thing going on, look at your top quantities, whatever they may be, see if they add up and equal one another. Look at your bottom quantities, see what they may be, add them up and see what they equal. Okay? That will give you a really good idea of what you should have up top and in the bottom. So that right there, that is an alpha decay. Let's look at a few others. Our next type of decay is a beta decay, but just calling a beta decay one thing is kind of a misnomer because we actually have 2 beta decays here. The first one we'll talk about is beta minus. For a beta minus decay, what we're going to get out of it is an electron plus an antineutrino. Did I just make up a word? Maybe. But a neutrino is actually a very, very small particle. They are ejected from stars pretty much non-stop. In fact, our own sun is putting out so many neutrinos that if you held up both of your thumbs, there are 1 billion neutrinos going just through your thumbnails every second. You just don't feel them because they are super, super small and they barely interact with anything. We were talking about this a while back. These are the same particles that if you had a light year's length of lead and you beamed some through, half of them would make it to the other side without touching anything. They're that small. This is an antineutrino, and we designate anti with the line on top of it. This means that it's neutrino, but it's antimatter neutrino. Okay? So our beta minus decay gives us the electron and an antineutrino. The way this will look if we write it, we're going to have n of some z and a, some element. It's going to yield to us some new thing. And since we know it's going to make for us an electron and an antineutrino, let's see if we can backtrack this and figure out what our new element will have to be in terms of its atomic number and atomic mass number. Well, I know the electron, it has a charge of -1. Now, normally for the atomic number down here, that's like how many protons exist. But for an electron, that's not a proton at all. But what we do here is we technically consider the electron as having an atomic number of -1. This allows us to conserve charge. That electron has a negative charge to it, a negative elementary charge, so we'll put a -1 down there. In comparison to protons and neutrons, the electron is effectively massless. So in terms of atomic mass number, we'll put a 0. I know that feels weird. How can you have an atomic number without an atomic mass number? Well, remember, the electron in and of itself is a fundamental particle. We're not obeying the same rules that we did when we had things in the nucleus for the proton and neutron. Furthermore, the neutrino here, it is so small, it is effectively massless for our equation. Do we believe it has mass? Yes. Is it extremely small? Absolutely. It is also a neutral particle. So for the neutrino, we don't put anything. It's just there. It's a byproduct. Okay? In fact, for a while, we weren't exactly sure if the neutrino even existed. It was only after we started looking at the star's energy outputs, like for our own sun, that we realized that without an extra particle, they'd be a few percentages off on their energy outputs. So the neutrino comes in and fixes that, which is nice. However, this means that if we look at our new element here, this n prime, if our atomic numbers and our atomic mass numbers have to add up, what we're going to have here for our new element is z plus 1 and a. Because this maintains that a equals a plus 0, which is great. Z plus 1 minus 1 is going to equal z. So we've once again conserved both charge and atomic number. And as a result, atomic mass number. So that's the beta minus decay. We also have, if you've got beta minus decay, you might as well have beta plus decay. Beta plus decay is very similar. You're still going to get an electron and a neutrino, except the matter and antimatter for them are going to flip. So instead of having an electron and an antineutrino, you're going to get an anti-electron, or a positron, and a regular neutrino. Notice how it's the beta plus decay, and you get the positive electron, or a positron here. As a result, if we have some element of Z and A, you're going to get some new thing, N prime, and then we're going to add to that a positron, which is an electron with a +1 charge to it, still 0 atomic mass, plus a regular old neutrino. So now, if we wanted to conserve charges, atomic number, atomic mass number, this is going to be Z minus 1 and A. Pretty straightforward in terms of balancing these equations here in our yields. The important thing to recognize, and just to help you remember this, is that the beta positive has a positive electron. The beta minus decay, which we see up here, has a negative electron, or a proper electron here, okay? So just slight difference right there. Now, something that we have that is rather strange, and it is very rarely brought up within the AP Physics 2 class, but it is something that exists, so we'll just put a star by it, okay? This is like not needed, but it's neat. I just like them because they're neat. There is something referred to as an electron capture. And an electron capture is exactly what you think it might be. What's going on here is that effectively what we have is, if this is some nucleus, this nucleus is getting big enough, or it's getting hungry enough, that some electron that's orbiting, or rather just in the electron cloud, is going to get bloop, eaten up. And when it gets eaten up, what we effectively have is this. We're going to have some initial element here of some Z and A. What we're going to do to it is we're going to add to it an electron, which, as you recall, is -1 and 0. This will yield for us the following. It is going to yield a new element of Z minus 1 and A, but we're also going to get out of it a neutrino. Effectively, these electrons bind, this electron that comes into the nucleus, it interacts with that nucleus, effectively eliminating it. The charge imbalance is gone, so it effectively removes that proton from play that it was brought in and interacted with there. So we get our Z minus 1 here because we effectively lost a proton. And then because we lost this proton and this electron, we need to output some energy somewhere, or even better, some matter in terms of an object. So we get a neutrino out of it. Like I said, we very rarely talk about electron captures in this class. It is something that is a little bit more rare than everything else, but they technically do exist, and it's best to just give you everything, okay? So that's what's going on for electron capture. Like I said, I just like them because they're neat. As for our last thing that is a big idea that we must talk about, we have our last decay, which is gamma decay. Why do I keep writing decay wrong? D-E-A-Y? This is a gamma decay. Now, you may have picked up on this based on prior videos that you've been watching or existing in this classroom, but this symbol we have used before. One of the ways we've used it is for a gamma factor for a Lorentz conversion, if you're doing like special relativity. We're not using it in that way now, but we've also used this symbol to represent something. That's something we've used this symbol to represent is a photon. Okay? And remember, a photon is just a photon of light. That's what we're representing here. Okay? In our case, this could be a photon with very high energy. Remember, for a photon, it has no mass. It has no charge. It is pure energy. That's it. Because of this, since there's no mass and there's no charge, we're not going to have a change in our element. Whatever we have is our like N in the beginning. Magnesium, lithium. That's all I got. Hi, like whatever. Whatever you have, it's going to stay as that. But something needs to happen here so that we release some energy in the form of this photon for a gamma decay. Normally what happens is the nucleus in and of itself is in an excited state. We've already talked about through energy level diagrams how electrons could be in excited state. And whenever these electrons drop, they give off photons in the form of energy. However, we can also have an excited nucleus. And if we have an excited nucleus, that nucleus could work its way to a ground state or a less excited state, and in doing so, it could give off some energy. Normally, these excited states happen either due to particle collisions, we've given some energy to the nucleus because it got hit by something, or there was a prior decay that left this nucleus with some energy. So maybe we had a fission where something split and one of the nucleus was still excited, and we're going to have another decay off of that. Okay? So when this happens, let's take an example here, and let's look at boron. Let's look at boron 512. Okay? So we're looking at kind of an isotope of this here. If we do this, this boron can decay downwards through a beta minus decay. Doing so is 13.4 mega electron volts. However, what it can also do is it can take a beta minus to here. This might only cost it 9 mega electron volts. But it still needs to get down. When it decays down like this to the beta minus, it's going to become carbon 612. When it decays through the top side, also through a beta minus, it is also becoming carbon 612. Both paths have left us the same new element. Except this carbon 612 through the top side has more energy in its nucleus. We put a star next to it. That is an excited nucleus for a carbon 612. Now we can undergo a gamma decay worth 4.4 mega electron volts, such that the total over here is equivalent to the 13.4 of going directly down. That gamma decay is often a transitional piece to get us down to proper energy levels. And the way it does it is that nucleus gives off light. As a result, the way we would write this is we'd write this as N star of Za yields NZa plus some gamma, some photon that came off. Where that photon is just pure energy. It's pure light. So the gamma decay is probably one of the easiest in terms of balancing, but it's probably one of the weirdest to think about in terms of having an excited nucleus either through a collision or through a prior decay, leaving that excited state there for the nucleus and having a secondary decay jump off of it. So it is possible as a result of this, as you see, to have back-to-back decays kind of chain their way down. And that's actually a very, very common thing that happens especially when we're running through fission products. And as we know, even if these decays take a long period of time, these decays will exist until you get to a Z of 82, which we know as lead, the last stable element to an indefinite period of time. Okay? So these are our decays that we care about for this unit in modern. We've got alpha, beta minus, beta plus, electron capture, which we really cares about, and then gamma decays. And we'll be using these moving forward as we see. Until then, we are finished here. Until next time, adios and take it easy.